All right, let's just jump right in. Every single time you flip a light switch or glance at your phone, really just living in our world today, you're plugging into this huge, invisible world of electricity. It seems super complex, right? But it's all governed by just a few simple rules. And today, we're going to deconstruct the code and figure out what makes it all tick.
Now, when you first look at something like this, yeah, it can seem pretty intimidating. It's just a whole web of symbols and strange terms. But I want you to think of it like a treasure map. And trust me, by the time we're done here, you're going to know exactly how to read it. We're going to learn the secret language of the networks that power, well, everything.
So our journey into this invisible electrical world, it has to start at the very beginning. We're talking the absolute basics. Because here's the thing. Every single complex system out there is really just built from a handful of simple but really powerful ideas.
Okay, so where does it all begin? What's the fundamental piece? The one tiny grain of sand that this entire electrical universe is built on? Well, let's go find out.
To understand any new world, you gotta learn the language first. And for electrical networks, that language really boils down to three key words: charge, current, and voltage. So, let's meet them. Everything, and I mean everything, starts right here, with charge. It's this basic, fundamental property of the particles way down inside every single atom. We're talking about those tiny, negatively charged electrons. They are literally the origin story for all things electric.
Okay, so if these charges just hang out and don't do anything, well, not much happens. But when they start to move, when they start to flow together, that is current. It's electricity on the move. It's the flow of charge actually getting up and doing something.
And this is a perfect way to picture what's happening on a crazy small scale. Just imagine all those little E symbols are our electrons, our charges. When they start moving through something, like a piece of copper wire, boom, that's a current. You can literally see them flowing from one end to the other.
But what makes them move in the first place, right? Something has to push them, and that's voltage. The best way to think about it is like electrical pressure. It's the push, the shove from a power source, like a battery, that gets that current flowing. Without voltage, all those charges are just a big crowd milling around with no direction. Voltage is what tells them where to go and gives them the push to get there. And this brings us to probably the single best analogy you'll ever hear for understanding electricity. Seriously, if you remember one thing, remember this. Think of electricity as water flowing through pipes. In that system, voltage is the water pressure, and current, that's the amount of water actually flowing. Just lock that picture in your mind. It's going to make everything else just click.
All right, so we've got the language of flow down. Now it's time to meet the components that actually control it all. These are the gatekeepers, the valves, and the switches in our electrical pipes.
And there are three main passive components. Now, passive just means they don't create power, they just manage it. And they are the resistor, the inductor, and the capacitor.
First up, the resistor. And its job is pretty much right there in the name. It resists the flow of current. But why? Well, look at this model here. On an atomic level, as those electrons are trying to flow, they're literally bumping into and colliding with the atoms of the material. It's like electrical friction, and that's resistance. Going back to our water analogy, a resistor is just like a narrow, pinched section in the pipe. It makes it way harder for the water, or the current, to flow through.
Next up is the inductor. Now, don't get bogged down by the super technical terms you see here. The simple way to think about an inductor is that it has electrical inertia. So, back to our water pipes. Imagine a big, heavy water wheel in the pipe. It's tough to get it started, right? But once it's spinning, it really wants to keep spinning. That's an inductor. It resists any change in the flow. It doesn't like speeding up, and it doesn't like slowing down. It just wants to keep things steady.
And rounding out our trio, we have the capacitor. Think of this one as an electrical reservoir. Its whole job is to just store up charge. It's kind of like a little battery that can charge up really fast and then release all its energy in a burst. In our water system, this is like a small tank. You can fill it up with water and then open a valve to let it all out when you need it.
Okay, so we've got the language, voltage and current. We've got the gatekeepers, resistors, inductors, capacitors. Now, we need the rules of the road, the two golden rules that govern how all of this stuff actually works together.
And these two laws come to us from a guy named Gustav Kirchhoff. And they are so simple, but they are unbelievably powerful. His first law, we call it KCL, is all about what happens to current when wires meet up. The second one, KVL, is about what happens with voltage as you go around in a complete circle.
Let's tackle KCl first. So you see this point right here where all the paths come together? That's called a node. And just imagine it's a T-junction in our water pipes. You've got some water flowing in and some water flowing out. Kirchhoff's current law is basically the super simple, common sense rule for what has to happen there. And the rule is, well, it's just this. What goes in must come out. That's it. You can't just magically create or lose water at a pipe junction, right? It's the same with electricity. You can't create or destroy electrons at a node. So the total amount of current flowing in has to be exactly equal to the total amount flowing out. Simple as that.
All right, on to the second golden rule, KVL. Now this one is all about any closed loop, basically any path that makes a full circle. Imagine you're an electron starting a little road trip around the circuit. You start at the battery, which gives you a big push of energy. Then, as you travel through the different parts, you use up that energy. KVL is just the law that keeps track of that energy balance.
And again, it's just a beautiful, simple rule based on conservation of energy. It says that on any round trip, all the energy gains you get from the power sources have to be perfectly canceled out by all the energy losses from the components. So by the time you get back to where you started, you've used up exactly as much energy as you were given. You're back to zero.
Okay, so let's take a breath. We've learned the language, we've met the main components, and we've got the two golden rules down. Now it's time to zoom out and see how this all comes together to build the world around us. Let's see the bigger picture.
Which really brings us to the most important question of all. What can you actually build with just these few simple ideas and two basic rules? You'd be surprised.
Well, you can build things like this. This might look complicated. It's called a Wheatstone bridge, and it's used for making incredibly precise measurements. But here's the amazing part. Every single line and symbol here is governed by the exact same rules we just went over. And it's not just this. From this little circuit to the microchip in your pocket, all the way up to the entire global power grid, it all comes down to the same handful of simple fundamental principles.
And that really leaves us with one final fascinating thought. These rules, they were figured out way back in the 1800s, but they are the foundation for the technology of today and of tomorrow. So the real question is, as our world gets more and more connected, more and more electric, what amazing new networks will these same timeless rules help us build next?